Hi everyone, I'm Mr. Fullerton, and today I'd like to take a few minutes to talk to you about friction. Our objectives: we're going to define and identify frictional forces, we'll explain the factors that determine the amount of friction between two surfaces, and we'll also determine the frictional force and the coefficient of friction between two surfaces as we look at applying our knowledge of forces and friction to a set of problems. So let's get started. First off, friction is a force. It opposes motion. Kinetic friction opposes motion for an object that slides along another surface. Static friction acts on an object that isn't sliding. Now, the magnitude of the frictional force is determined by two things. It's determined by the nature of the surfaces in contact, and you've seen that before, right? If you're walking with very slippery shoes on ice, you have much less friction than if you're walking on dirt with cleats. The nature of the surfaces in contact provides a different amount of friction. We characterize that with this value known as mu, which we call the coefficient of friction. And secondly, the magnitude of the frictional force is determined by the normal force acting on an object, Fn. Now, the coefficient of friction we can find by taking the ratio of the frictional force divided by the normal force. It's an empirically determined value. And usually you can look up the coefficient of friction for different types of objects. Now, if an object is sliding with kinetic friction, it may have a different coefficient of friction than static coefficient of friction. And almost always the kinetic coefficient of friction is less than the static coefficient of friction. That means there's less friction for something sliding than if the object is not sliding, if the object's at rest. So, for example, it takes more force to start a object in motion than it does to keep it in motion as long as it's sliding. Think of pushing a couch along a floor. A lot harder to get it started than it is to keep it in motion. Same idea here. So you can use these approximate coefficients of friction in solving problems. Now, in choosing the coefficient of friction, you've got to be careful whether you want to pick the kinetic coefficient of friction for sliding objects or the static coefficient of friction for objects that are not sliding. Let's take a couple examples. For a sled sliding down a snowy hill, well, we've got sliding there, so we want the kinetic, or mu sub k, the kinetic coefficient of friction for sliding objects. For a refrigerator that's at rest that you want to start moving, well, it's not sliding yet, so you want the static coefficient of friction, mu sub s. How about a car with tires rolling freely? This one's a little bit tricky. You have to think about what happens where the tires contact the road. As the tires contact the road and lift up, they're not actually sliding. Therefore, we'll use the static coefficient of friction, at least at the first pass level. Later on, you may even look at something called the rolling coefficient of friction, but we're going to stick with just static and kinetic for now. And how about the same car if it's skidding across the pavement, if the wheels are locked? Well, in that case, you have sliding friction, so that again would be mu k, the kinetic coefficient of friction. Let's put this into practice. We have a car's performance tested on various horizontal road surfaces. The brakes are applied, causing the rubber tires of the car to slide along the road without rolling. The cars encounter the greatest force of friction to stop the car on. We have four choices: dry or wet concrete and dry or wet asphalt. Well, let's use our coefficient of friction table, and because it's sliding without rolling, let's use the kinetic coefficient of friction. Which is the greatest? Which will give you the most friction? Well, in this case, of all of the values, the highest one is rubber on dry concrete, right here, 0.68. So our answer must be 1, dry concrete, because you have the largest coefficient of kinetic friction. Now, in calculating the force of friction, remember the force of friction depends only upon the nature of the surfaces in contact, that coefficient of friction, as well as the magnitude of the normal force. And we can quantify this mathematically as force of friction equals mu, the coefficient of friction, times the normal force, Fn. We can combine this with what we've already been doing with Newton's second law and free body diagrams to solve some more involved problems. And instead of talking about it a whole lot, maybe it makes more sense to do a couple more examples. So here we have a diagram showing a 4 kilogram object accelerating at 10 meters per second squared on a rough horizontal surface. Find the magnitude of the frictional force acting on the object. Well, a great place to start here is our free body diagram. So our free body diagram, we can draw a dot or a box to represent our object, and let's show all the forces acting on it. We have gravity pulling it down, mg. We have the normal force from the surface it's on, pushing it back up, and we know because it doesn't accelerate vertically, up or down spontaneously, that those must be equal. We have an applied force to the right of 50 newtons, and we have a frictional force to the left. Now, our next step, let's use Newton's second law to figure out what's going on here. Since we want the frictional force, that's in the x direction, so let's start by writing Newton's second law for just the x direction. The net force, or the sum of all forces in the x direction, is equal to the object's mass times its acceleration in the x direction. Now, we can replace our net force in the x direction by the sum of all forces acting in the x direction. If I call to the right positive, then what I have is F app to the right, F applied, minus the force of friction must equal max. What I want is the force of friction, so let's solve algebraically for that. Force of friction, therefore, must equal F app minus max. Now I can substitute in my applied force, 50 newtons, minus my mass, 4 kilograms, times my acceleration, 10 meters per second squared, for a total of 50 newtons minus 40 newtons, which is 10 newtons. Therefore, the frictional force must be 10 newtons, and that, of course, is to the left. Let's take a look at another one. Horizontal force of 8 newtons is used to pull a 20 newton wooden box moving toward the right along a horizontal wood surface. And we know the coefficient of kinetic friction for wood on wood is 0.3, given in the problem, or you could look that up on a table. We're asked to find the frictional force acting on the box. Well, let's start by drawing our free body diagram. We have our object, dot or a box. We have an applied force, I'm going to call that F applied, of 8 newtons to the right. We must have a frictional force in the opposite direction, opposing motion, gravity pulling it down, mg, and the normal force from the surface pushing it back up. We're asked to find the frictional force acting on the box. Well, it tells us the box has a weight of 20 newtons, so we know mg must be 20 newtons. And because the box does not spontaneously lift off the table or go through it, it can't accelerate in the y direction, so it's safe to say the normal force must balance that and also be 20 newtons. So then the frictional force is given by mu Fn. In this case, it's the coefficient of kinetic friction, mu k, so that's going to be 0.3 times our normal force of 20 newtons. That comes out to be about 6 newtons. Good. How about the net force acting on the box? Well, again, in the y direction, it's easy to see that there will be no net force. It doesn't accelerate in that direction. So we only have to look in the x direction. The net force in the x direction is always equal to max. And we'll replace net force in the x direction if we call to the right positive by our applied force, 8 newtons, minus our frictional force, Ff. 8 newtons minus our frictional force we just figured out is 6 newtons, so we get a total of 2 newtons as our net force in the x direction. Now, number 3, find the mass of the box. Well, we already know the box's weight is 20 newtons. So we write weight as mg is 20 newtons. Let's solve for m. M must equal 20 newtons over 9.81 meters per second squared. 20 newtons over 9.81 meters per second squared gives me a mass of about 2.04 kilograms. And finally, find the acceleration of the box. Well, acceleration is the net force over the mass. It's only going to accelerate in the x direction, so let's make that the acceleration in the net force in the x direction. We found net force in the x direction as 2 newtons previously, so that's 2 newtons divided by our mass, 2.04 kilograms, or roughly 0.98 meters per second squared. Great. Another one. Compared to the force needed to start a crate moving across a rough level floor, the force needed to keep it sliding once it is moving is either less, greater, or the same. Well, remember, the coefficient of kinetic friction, the coefficient of sliding friction, is almost always less than the coefficient of static friction. So less force, less friction to keep something moving than to start it moving. Therefore, the answer here must be number 1. The force required to keep it sliding is less than the force to start it sliding. One last problem. An airplane moving with a constant velocity. Ooh, constant velocity. Right away I'm thinking constant velocity means acceleration is 0. Therefore, the net force must be 0. In level flight, compare the magnitude of the forward force provided by the engines to the magnitude of the backward frictional drag force. Well, once again, if there's no net force, all the forces must be balanced. We have a forward force provided by the engines, a backward force provided by the frictional drag. If there's no acceleration, they must be equal or the same. Hope that helps with friction. Give a couple more sample problems a try, and if you need more help, want more practice problems, things like that, check out aplusphysics.com. Thanks for your time and have a great day.